All right, today we're diving deep into one of the most essential parts of any computer, its memory. We're going to peel back the layers and see exactly how these amazing machines manage to store and recall information, from their permanent archives to their super-fast temporary workspaces.
So it all boils down to this one question, right? How does a hunk of metal and silicon actually remember stuff? Well, it's not magic. It's just some seriously brilliant engineering that gives a computer two different ways to think, a long-term memory for the essentials and a short-term memory for what it's working on right now. To really get it, you've got to meet the two main players in the story, ROM and RAM. Just think of ROM as the computer's permanent library. It's full of books with crucial information that never, ever changes. RAM, on the other hand, is the total opposite. It's like a whiteboard, a temporary workspace that's constantly being written on, erased, and rewritten as you go.
So let's start with that permanent library, read-only memory, or ROM. This is the stuff that gives a computer its basic identity. It's what tells it how to wake up and get started in the first place.
I mean, the name really says it all, doesn't it? Read-only memory. This is where permanent info lives. And the really critical part? The data stays put even if you pull the plug. We call that non-volatile memory. And it's absolutely essential for things like your computer's basic startup instructions.
So how does it hold onto information so permanently? Well, ROM isn't just a storage container. The information isn't just saved there, it's physically built into the hardware itself. You can think of it like the information has been set in stone, or, more accurately, in silicon.
Here's kind of how it works. Picture a grid where every connection has a tiny microscopic fuse. When it's brand new, all the fuses are intact. Everything is connected. The programming process then sends a very precise electrical jolt to blow specific fuses, breaking those connections for good. The pattern of broken and unbroken fuses that's left behind creates a permanent pathway that represents the data. It's pretty cool.
Okay, so that covers the permanent library. Now let's flip over to the other side of the computer's brain, that busy, temporary workspace we call RAM, or random access memory.
Unlike ROM, RAM is all about being flexible. It holds data temporarily. It needs power to remember anything. But the trade-off is that it can be written to and read from with incredible speed. And that random access part, that's the secret sauce. It means the computer can jump to any spot in the memory in the exact same amount of time, which is what makes it feel so snappy.
So how does that work in practice? Well, writing to RAM is a super fast three-step dance. First, the computer sends the exact address where it wants the data to go. Second, it puts the actual data onto the input lines. And third, it zaps it with a write signal, which is basically like hitting the save button for that one tiny cell, all in a fraction of a second.
And reading data. It's pretty much the mirror image. The computer sends the address, activates the read signal this time, and bam, the info from that cell is instantly available on the output lines for the rest of the system to use. It's simple, it's elegant, and it is unbelievably fast.
Now, you might be thinking, okay, RAM is RAM, right? But this is where things get really interesting. See, inside the world of RAM, there's this constant battle going on between different engineering priorities, and it leads to a really important trade-off. This battle is a constant tug-of-war between three things: speed, cost, and density, like how much memory you can cram into a tiny space. And this whole conflict is perfectly captured by the two main flavors of RAM: static RAM, or SRAM, and dynamic RAM, or DRAM. Let's just walk through this. SRAM is pretty complex. It uses 4 to 6 transistors for every single bit of information. DRAM is way simpler, using just one transistor and one capacitor. Because of this, SRAM holds data rock solid as long as the power is on. DRAM, though, it's kind of like a leaky bucket. It needs to be constantly refreshed, or it'll forget what it's holding. So what's the result? A clear trade-off. SRAM is crazy fast, but it's expensive and bulky. DRAM is slower, but it's cheap, and you can pack a ton of it into a small area. And that is why every computer uses both. A small, pricey, lightning-fast chunk of SRAM as a cache right next to the processor, and a huge, cheaper block of DRAM for its main system memory. Here's another way to picture it. SRAM is like a light switch. It's either on or it's off. It's a solid, stable state. Super fast, but all those parts take up space and cost more. DRAM is more like that leaky bucket. It's simple, it's small, which is great, but you have to keep topping it off, refreshing it, so it doesn't lose the information it's holding. So we've got the individual building blocks now, but how do we get from one tiny memory cell all the way up to the many gigabytes of RAM that you find in your computer or your phone?
First, let's just take a second to appreciate the scale we're talking about here. Because computers work in binary, our units are all based on powers of 2. So a kilobyte isn't 1,000 bytes, it's 1,024. A megabyte is over 1,000,000, and a gigabyte is over 1,000,000,000. We are wrangling immense numbers of these tiny, tiny cells.
Now, you just can't build one single gigantic chip to hold all that data. It would be an absolute nightmare to design and manufacture. So instead, engineers got clever. They build arrays of smaller, identical memory chips and figure out a way to make them all work together as a single team. Here's a perfect example. Say you want to build a 256 kilobyte memory system. You could start with 4 smaller 64 kilobyte chips. Then you add a special circuit called a decoder, which acts like a traffic cop. When the computer asks for a memory address, the decoder instantly knows which of the 4 chips has that address and activates just that one. As far as the computer is concerned, it just sees one big, seamless 256K block of memory. It's a really smart way to scale things up.
And that really brings us to the most important takeaway here. A computer's memory isn't just one thing. It's this complex, carefully balanced system, a whole ecosystem really, that's built on a constant negotiation between the permanence of ROM, the speed of RAM, and the never-ending trade-offs between cost, speed, and size.
You know, for half a century, that balancing act has been the engine driving innovation in computers. So the real question now is, what's next? As our hunger for more data and more speed just keeps growing, what new technologies and new designs are going to define the trade-offs for the next generation of memory? That's definitely something to think about.